Omar?
Yes, Doctor. I have a question before starting.
Yes. Go ahead.
When will be the grades of the midterm?
إذا خلصتم صح.
اوكي بس قصدي تقريبا يعني.
إذا خلصتم صح.
تمام يعطيك العافية.
Okay. Welcome to E21. Today's lecture will be the 25th lecture. And in today's lecture, we're going to, if you remember what we started with last time, we started with chapter 9, and we said like in chapter 9, we are interested in sinusoidal sources instead of sources that are DC, that are of DC nature. So it turns out that, well, if you want to deal with sinusoidal sources, it would be much similar to handle the quantities, meaning that the voltage and the current, if you kind of like move to another domain and then do all of the analysis in that domain. So usually, if you have a circuit like this, and when you try to analyze it, you see that you'll have a mixture of differential and you'll have a differential equation. So if you want to, for example, study the current I, you will have a differential. I mean, you need to solve a differential equation, where in this fact or in this time you need the forcing factor. It's not going to be constant anymore. It's going to be something of sinusoidal nature. It turns out that if you take this problem and say like convert it from real numbers to complex numbers, then you will see that the problem is, and do all of the analysis in the complex number domain, you will see that everything is now straightforward. Although, I mean, the downside of this this approach is that you have to deal with complex numbers, which is usually not something that's pleasant to deal with. But it's much simpler, much faster, and it lends itself to something that we are all familiar with. So what we will see, inshallah, in this chapter, that the problem that, or the techniques that we studied in chapter 4, chapter 1, chapter 3, 2, 3, and 4, they could be easily applicable if we can move this circuit to complex domain, we call phasor domain, and then analyze it over there. And if we want things in time domain, we can transfer it back. It's not something that complicated. But the key element here is knowing how to deal with complex numbers. And I'm assuming that you've studied this in Math 001. Am I mistaken, or did you study complex number in Math 001? Abdullah?
Yes, we have studied before in the 001.
Okay, good, very good. Okay, but before we need to deep dive into some of the techniques, or some of the forms of complex number that we find it much simpler to handle such complicated problems. So let's start by defining some notation. So if we have a sinusoidal source, then it's very important that you represent it with complex representation. So what do we mean by complex number representation? So we have a source that's Vm cosine omega t plus phi, and we want to do some sort of transfers into something in the complex or with complex number. It turns out before we deep dive into how to do this representation, it turns out there are two general forms of two common forms of complex number. There's something called the rectangular form, and the other thing is called polar form. So in a rectangular form, this is the form that we are all familiar with. If you have a complex number, then it can be decomposed into two components, the real component and the imaginary component. So z equals to a plus gb, a plus jb, and j here is square root of 1. Remember, in math, this is square root of 1 is I. But in electrical engineering, we usually use J because to differentiate it from the current. Okay, this is the rectangular form. This is the form that we are all familiar with. The polar form is somehow, it's kind of like, I mean, if we are to plot this one, it doesn't tell us the angle between, it doesn't directly tell us the angle between between the real and the imaginary part. So if we want to draw it in the complex domain, in the complex plane, you will have the real part here, the imaginary part here. So A is the real part, say A is here. B is the imaginary part, B is here. So the vector ZA plus JB is this one. So this vector has a length, C, and has an angle that meets with the real axis. So the rectangular form doesn't tell us directly these two pieces of information. So in order to do that, we need to do a transformation to something called the polar form. So if we have a complex number, z equals to a plus jb, then it could be written as the following: c multiplied by e to the complex, e to the power j theta, or this is the general form, and this is one of the representation of that one. So you may ask yourself, what is C? C is the length of the vector. So if you have a vector, the length of that vector is going to be square root of the first component plus the second component squared. And this is exactly C. Theta is the angle between the imaginary part and the real part. It's actually, this is the angle that that complex vector is making it with the real axis. So the inverse tangent of B minus I, B over I. So one of the very fundamental identities of Euler's identity, and it says that if you have a complex exponential, e to the power j theta plus or minus, then this one could be decomposed into cosine theta plus, if the sign here is plus, j sine theta, or minus if the sign here is minus, j sine theta. Is it clear, Shabab? Okay. So let's apply Euler's identity to the, we want to convert this one to a rectangular form. So remember, the polar form captures the magnitude and phase. The rectangular form captures the real and imaginary part. So what we need to do, we need to use Euler identity to write e to the power j theta as cosine theta plus j sine theta. So if we multiply cosine theta plus j sine theta then you will see this is A, this is B. So you'll end up with A plus G, JB. Is it clear? Okay, let's see what we have. So this is exactly what I'm saying. What I'm saying that if you have a complex number, then it could be represented as a complex vector in the complex or in the complex plane. So the complex plane has the x-axis is the real axis, the y-axis is the imaginary axis, and the length of this vector is c. The angle that this vector is making with the real axis is theta. And you can see here that c is square root of a squared plus b squared. This comes from Pythagorean theorem. Okay, so now we know the complex. We know that. Well, we know that there are two basic representations for complex numbers. The first one is in the rectangular form, where we have access to the real and imaginary part. The second one is in the polar form, where we have access to the magnitude at base. Now let's see, before actually we know which form to use, let's see what kind of let's deep dive into some of the on the impact of the angle between that this vector is making with the real axis. Okay, so what we have in here, we have 4 different complex numbers. All of these 4, they have the same length. So the magnitude is 5 in all of them, but you see here that each vector is making a different angle with the real axis. So if the real and imaginary part are both positive, then this vector will be in the first quadrant. If the real part is negative, then it's going to be in the second. If both are negative, then they're going to be in the fourth quadrant. If the imaginary axis is negative, then it's going to be the fourth quadrant. Okay, so there's something ambiguous here that we need to actually account for. If I tell you what is cosine of let's take an angle here. Cosine of 60 degrees. What is cosine of 60 degrees?
Half.
Half, exactly. What is cosine of 360 degrees plus 60 degrees? Also half. What is cosine of 2 multiplied by 360, which is 720 plus 60?
Does not change. Also half.
You see here, what is cosine of minus 360 plus 60? No. Again, it's going to be half. So you see that there is a complete rotation. So if you rotate the phase by 360 degrees, you will get to the same point. So if you give me this vector, 4 plus j3, then in this case, and you tell me what's the angle between the magnitude is unique. It's going to be 5. But the angle, I can have infinite, I have infinite number of angles. So I can say 60, I can say 360 plus 60 minus 300. It's exactly the same. I'm referring to the same angle. This is exactly the angle that the vector is making with the real axis. So we need to somehow restrict our analysis to a specific interval. And let's see what we have in here. So a complete rotation in the complex plane corresponds to 360 degrees. This is in degrees, or 2 pi shift in the angle, which implies that we have an infinite number of possible angles. For example, here, this is a complex vector, and the magnitude of this one is 1. The phase is 45, but if I write it 45 plus 360, which is 405, plus 2 multiplied by 360, which is 765, minus 360 minus 2 multiplied by 360, I will get exactly the same vector, or the same complex number, the same representation. So it's this 360 degrees. The ambiguity in the phase is something that we need to restrict. And as a matter of fact, this ambiguity in phase is very crucial, because it's in some applications, this is what limits the applicability of your system. So you see that sometimes your system will say like, well, I cannot do any, for example, fine localization because of this ambiguity in the phase. So you need another thing to account for if you want to get an accurate location, for example. Okay, so what we're going to do, we're going to actually restrict our angles, enforce our angle to be within this region. So it's going to be between minus 180 to 180, or between minus pi to pi. So any angle that you have, if I tell you what's the angle between, what's the angle of this vector, then you will see that, well, I have infinite possibility, infinite number of angles, but only 45 degrees is within this interval, between minus 80 to 180. Okay? So now what happens if you have an angle that's greater than 180? If you do the calculation, because some calculators, or most of the calculators, they will give you the angle from 0 to 360. Or sometimes if you do that, you will see that when you use polar form, you're going to add the angle if you're multiplying. So you will end up with an angle that's greater than 180. What should you do? What do you think about it? Ibrahim?
Maybe we should subtract 360.
Exactly. So what you need to do here is keep subtracting until you get inside the interval. As an example here, so what we need to do, we take the angle 765, then subtract 360 degrees. So we'll end up with 405 degrees. This is outside. So we need to do another subtraction. So 405 minus 360. And you see that this one is 45. So this is inside. Now, what happens if the angle is less than 180? You get, for example, minus 360. So you need to keep, in this case, you need to keep adding 360. So this one is going to give us 315, which is outside. Then we need to actually also add 360, and this going to give us 45 degrees, which is inside. So the moral of this story is like the following. So the angle, we need to restrict it to the interval minus 180 to 180. If we are outside this interval, if we have a value that's greater than 180, then we need to keep subtracting 360 until we get inside the interval. If we are outside this interval, but the value is less than 180, so we need to keep adding 360 degrees until we get inside the interval. Okay. Another important complex number is the conjugate of the complex number. So we have a complex number, and we are sometimes interested in its conjugate. And this is very important when we talk about, we're not going to talk about it in this course, but maybe in E to 13. When you talk about maximum power transfer to a load, you see that this condition occurs when the load resistance, when the impedance of the load is the complex conjugate of that. So knowing the complex conjugate of a number is very important. So how to find the complex conjugate? So if you have a complex number, then you need to change the sign of the negative or of the imaginary part of it. So this is a complex number. So what impact does this what impact does this has to do with the polar representation of complex number? It will only change the angle here. So the angle used to be positive, so it's going to be negative. For example, N2, this is the this is the complex conjugate of N1. So you see the real part is as it is, it doesn't change. The imaginary part is the sign of that is changed. So the angle here is negative. Similarly, N2 is actually the complex conjugate of N. This one is the complex conjugate of that one. So we can conclude that there is a reflection about the real axis. Okay. So now what did we do? So we defined the two representations, the rectangular and the polar. We said that we need to be careful when we choose the angle and the polar coordinate and the polar form, because we have infinite possible number of angles. So we have to somehow restrict this analysis to a specific set of angles. Then we studied the complex conjugate of a complex number. Now let's see what can we do if you want to add two complex numbers or subtract two complex numbers. So if you want to add z1 plus z2, you'll see that you need to add the real part separately and add the imaginary part separately. So in this case, you will get 20 plus j 30. If you want to subtract Z2 from Z1, then you need to subtract the real part separately and subtract the imaginary part separately. It's going to be minus 3, minus 16, and this is going to be 4, minus J. Okay, this seems straightforward. But now this is, the other one is rather complicated. Not that much, but it's somehow, it's not as straightforward as the previous one. So we need to add and subtract complex numbers. But in this case, these complex numbers are represented in the polar form. What should we do, Mohammed?
We should first find the real and the complex part.
Yes. And then do the addition and subtraction. So this is, I mean, in some of the calculators, you can do that directly, actually. You can add and subtract with complex, with polar form in some of the new calculators. I mean, you don't need to do this addition or this step. But if you're doing it by hand, or for most calculators, you cannot do this. So you need to convert to rectangular form. Again, you remember, you can do that with your calculator. Your calculator will allow you to do that. There's an option converting this to converting polar form to rectangular form. So if you do this conversion, you get minus 3535 minus K 3.535. Does it make sense? Does this value make sense? Danny?
Yeah, Doctor, what's the meaning of this sign, the angle sign?
It's negative.
So it should be 10 negative 53.13 or minus?
No, you mean this one?
Yes.
Oh, this is just the angle. It's just like instead of writing it with complex exponential, you write it with the angle.
Can you write it in a different way so I can understand?
Yes.
Mm-hmm.
This tells you that this is the angle. Okay, good. Ziad, what's in?
Is it correct to say that the real part is the cosine of the angle and the sine is the?
Yes, that's exactly. The real part is the cosine. The imaginary part is the sine of the angle. Yes, exactly. That's what we've been doing. Because remember, this complex exponent. So using Euler's identity, we have cosine of the angle plus j sine of the angle. Okay, so does this value make sense to you, Sharon? Just by looking into them. So this one is in which quadrant do you want?
The first.
The first one, صح?
Yes.
Okay, so this is the first one. Since it's the first one, what should be the sign of the real and imaginary part here? Hadi?
Both are positive.
Exactly. Both are positive, so we're getting positive, so it makes sense to us. Now, what about the second one? In which quadrant, this one? Yes, sir?
Yes, it is in the fourth quadrant.
Why?
I mean third. My bad. I mean third quadrant
Third.
because both are negative. Third.
Yes. Yes, because if you think about it here, this is negative 90. This is negative 180. So it's going to be in the third quadrant. So both are negative, which makes sense to us. Okay. So now we convert everything back to, we convert everything to rectangular form. So we need to add them up. If we add them up, we'll end up with 2.465 plus J 4.465. And if we take the convert them to polar form, we get so yes, eventually you want to represent them in the polar form, but if we want to do the addition, then you need to convert them to rectangular form, add them up, take the final answer, convert it back to polar form, and this is the final answer. Aziz?
So how to convert it to the polar form?
There are two options. The first one is using calculator. The second one is actually you take the amplitude, so you square. For example, here, we're going to take this one. You take 2.465 squared plus 4.465 squared, and this can give you 5.1. Then you take
tan inverse.
Tan inverse of 4.465, 2.465, and this is to give you 3. But
Okay, very clear.
okay, but this might be in radians, so you have to make sure that your calculator is not mixing gradients with degrees.
Yes.
Good. Ahmed, Al-Jishi, question?
You just answered it.
Okay, what was it?
It was about if the question gave me the angle in radian. Do I have to convert it to degree first to calculate it, or I can just use the calculator?
It depends. It depends on your calculator, actually. You set your calculator to work on degrees, then you need to convert that angle to degrees. If you set your calculator to work in radians, then your calculator will take care of it. But make sure that you're aware of what angle system that you have.
Thank you.
Now, the interesting part is what happens if you if you want to multiply two complex numbers. So you have two options. The first one is actually if you multiply Z1 by Z2, so you take Z1 8 plus J10, and Z2 which is 5 minus J4. So if you multiply them up, 8 by 5, 40, J32, 50, J50, then plus 40, you will get 80, plus J18. And if you convert it to the polar form, you'll get 80 to 12.68 degrees. Okay, this is one option. The other option is, well, this is simple to us. This is just multiplication of 2. But if you have huge number of them, 3, 4, 5, or any other number, you will see that it will make more sense. It will be much simpler if you convert everything to polar form. So if we go to the first one, it's going to be 12.81. The angle is 51. Z2 will be 6.4. The angle is minus 38. Now, so Z1 multiplied by Z2. What should we do? What do you think we should do? So it turns out if you write everything in polar form, you will end up with the following. So if you want to multiply two complex numbers written in polar form, then you multiply the amplitude and you add the angles. So we multiply the amplitude, 12.81 divided by 6.40, and you add the angle, 51.34 minus 38.66 degrees. And if we do that, we'll end up with 82, 12.68 degrees. Then if you want to convert it back to polar form, to rectangular form, you need to do that. Any questions about the Aziz?
Doctor, is J square equal to -1?
Yes.
No.
Okay. So now what happens if we have complex numbers and we want to divide them? So remember, if we want to add or subtract complex numbers, it's usually better to do it in the rectangular form. If we want to multiply them, then we need to it's better to do it in the polar form where you multiply the amplitude and you add the angles. If you have complex numbers and you want to take you want to divide them, then you have two options. The first one is you do it in rectangular form, but in this case, so what you need to do is you multiply both sides, the numerator and denominator, by the complex conjugate of the denominator. Okay, so this is the solution. In rectangular form, or in polar form, you take the amplitude of those, 2.12, 45 degrees. So notice here two things. The first one is whenever the real part and the imaginary part are equal, the angle between them is 45 degrees. And the magnitude will be, you take one of them, multiply it by square root of 2. If you take 1.5 and multiply it by square root of 2, this is going to give you 2.12. But you see that the point here, when you divide them, so you need to take the complex, you multiply the numerator and the denominator by the complex conjugate of the denominator. The other option is actually to convert it into polar form. In this case, Z1 will be 6.71, the angle is 26.57 degrees. Z2 is 3.16. Now, if you remember when we did multiplication, when we multiply two complex numbers, we multiply the amplitude and add the phase. Here we're going to divide the amplitude and subtract the phase. So Z1 divided by Z2, it's going to be 671, 26.57 divided by 3.16. And you realize that this one is 2.12, the angle is 40 degrees, so it's going to be 1.5 plus K angle. Clear, Shabab?
Yeah.
So some useful identities here. If you take the square of J here, so this is actually derived from the fact that J squared is actually -1. So this is the identity here. So if you take -J and multiply it by J, you'll get +1. If you have J in the denominator and you want to move it to the numerator, then you will get minus. Again, this is duplicate. If you have e to the power plus or minus j pi, this is going to be negative. This is clearly from the fact that e cosine of pi plus or minus j sine of pi. And this one is always 0, pi is 180, so sine of 180 is 0. So cosine of 180 is -1. This one comes from the fact, again, cosine y over 2 plus or minus j sine of y over 2. So cosine of y over 2 is always 0. This one is always 1. So you will end up with the plus or minus j. Okay, so the last piece of information that I want to share with you is this one. Yes. If you multiply a number by its conjugate, then the result will be a real number. And the result is going to be the amplitude squared, or the magnitude squared. If you add a number with its complex conjugate, you will get a real number, which is equal to the real part of the complex number. If you subtract the number with its from its complex conjugate, you will get the you will retain the imaginary part scaled by 2. If you want to, if you divide the number by its complex conjugate, you will get 1 and the angle is 2 theta. So think about it this way. If you have a number, then it has c theta. The complex conjugate is going to be c minus theta. So if you divide them, you will end up with 1. theta minus theta, because that's exactly what you did. Any questions, Shabab? Okay, that's it for today. Thank you very much, and كل عام وانتم بخير، نشوفكم إن شاء الله بعد الإجازة.
كل عام وانتم بخير، جزاك الله خير.
نعم.
انت بخير.
الدكتور بخصوص جريد سكوب حق الكويز.
I will do it now.